In this lab, we're going to begin studying methods for experimenting, with dynamic systems. Whenever we are studying dynamic systems in the laboratory, this often requires us to, not always, but sometimes we want to introduce some sensing. And because the signals that we measure can be time varying, we often want to have some way to acquire data. And so we want to measure those signals because they might have some information of interest to our understanding of the system and so on. What we do in this lab is use a basic compound pendulum, shown here, and it motivates a couple of different things. First is of course reviewing how we model the dynamics of the pendulum itself, and we introduce a really simple potentiometric sensor to measure the angle of motion of this pendulum. Keep it very simple so we can focus on just some of the methods that we use for collecting data. And one of the goals of the lab is to introduce how we can use Arduino especially and Python together to kind of form a simple data acquisition system. We also want to learn about why this is useful in some cases, and there's some limitations too that I'll mention in some of the coming the videos. So we want to look at some of the common tasks that we undertake when we're studying dynamic systems, such as, again, proper data collection, the modeling, but also in this case we'll look at how we can estimate some of the parameters that we might use when we're building this model here. Okay, so we'll talk about that. As in all our labs, we try to have very specific goals that we introduce. For example, we practice modeling a system, learn about sensors, how to use them, how to apply methods for measurement of signals and analyzing them. We want to also develop good practice for just developing an experiment and how to use the model to help us understand. And then, of course, we want to maybe answer some specific questions to make it interesting. So, for example, we might want to know if we had that model and we refined it through experiment, can we use it to predict the response? One of the things we're going to find with this setup is there is some friction present that's introduced by the sensor, and we want to use that as an opportunity to see if we can estimate what the friction coefficient is. Okay, and in all the labs in this course, we have us interacting with the setup, also with Python, now using a serial communication with the Arduino to collect data from, in this case, a nice simple little rotational potentiometer. This potentiometer, of course, is connected to the experimental setup, right? So learning how to put these together in a meaningful way is part of the lab. The dynamic response of this pendulum, the way we study it, is pretty simple. You release it from rest, and you can see here the pendulum has been held at about 90 degrees. At some point you release it and it's just going to decay, right? It's going to stop, and right here at 0, and the pendulum actually stops. It's that friction in the bearings and in the potentiometric sensor itself that actually brings it to a stop. Of course, there's a little bit of wind drag, but that's very small. We don't think that plays as large a role in this setup as the friction in the bearings. And looking at the decay of this, and again, being able to measure the data, all of that is just what we're trying to practice here. Later on, we'll study, how we can extract useful information, also how the signal decays. Just as a reminder, of a simple pendulum model. We'll go through this again when we're talking about simulation in a related video, but the simple pendulum, right, it has a fixed axis of rotation about a pivot, gravity's acting, and we basically apply a Newton's law about that pivot, here. So we say that the rate of change of the angular momentum h, or h dot, is also equal, because omega, right, is equal to theta dot. So h dot is j omega, remember that, basic relations. So h dot is j theta double dot, if you like. We won't necessarily use the equations in this form, but just reminding you of different ways that this might be written, and you might see it in different references, other videos and books. And that's, again, by Newton's law for fixed axis rotation. the sum of the torques about that pivot, right? In this case, if we assume that the only torque that's acting is, and we're going to call this tau theta, that's what we call the gravitational restoring torque. It's the torque that wants to bring it back, right, and settle due to gravity, and that's the mgl sine theta, right? This sine theta is what makes this simple resulting second order ODE that's very commonly seen in physics books and so on. It's a nonlinear differential equation. Again, we won't necessarily study this form. We'll look at it in different ways, but we're going to get into state space representations. Also, contrast the simple and the compound pendulum. The major difference here is that the moment of inertia for a simple pendulum, which is again a rod that's we assume is massless with a simple mass at the end, that's your simple pendulum, and so the moment of inertia is ml squared. Here we're giving you an opportunity to study the compound pendulum, which has distributed mass, right? This has some shape, and based on where the CG is and the point and the pivot location, we want you to find, what is the effective moment of inertia. The only way that changes in the equations, right, is going to be in this term here. Again, you're going to have now the length to the center of gravity, which might be somewhere, different from, of course, the mass location. So these are just some things to think about, and as a review of things that you might have seen in a previous dynamics class. Okay. There can be other significant torques on this system. Again, this is all, the purpose of this is to help think about how we model systems and rotational systems and so on. Here, just to remind you, if you want to add additional effects from different torques, we have again, h dot is the variable that's changing. It's the rate of change of the momentum, angular momentum, and it's just the sum of the torque. So we already know about the gravitational restoring torque. We might have some friction torque that's added here, right? And note the direction. If this guy's moving in this direction, then the frictional torque is always going to oppose it. But if it starts moving in this direction, that friction torque changes, and we'll talk about that when we're actually building a simulation. This TA might be some applied torque. Maybe you had a motor or something on here. This is just a little schematic of the pot, right, the potentiometer. If you had a motor on here, that might apply another torque on here that maybe moves it and positions it, right? We're going to talk about how we model this frictional torque. One way is with this signum function. I'll talk more about that in a related video. Okay. Finally, in this lab, what you want to do is, the big purpose of it is to compare the model, the simulation that we can build, given whatever parameters we have with experimental data, bring those two together. And I'll be talking, in lab, you'll be talking about how do I read in any measured data from your potentiometer that you've calibrated and adjusting that measured data so that it looks just like what you might simulate. And like this shows an example, and you can take a look at these slides later. If you line these up, you can actually start playing around with the parameters that you have and try to match them up. And in that way, you can make the model match, right, the experiment. And you can identify, for example, the effect, what is the primary source of friction in this in this setup, right? Is it due to certain effects and so on, right? So this little slide here just tells you how a process that you'll go through after you run the lab for comparing the simulation and the measured data. And I will talk more about that in a related video.